In the silent void of space, the universe reveals secrets that defy our imagination. Strange objects, cosmic phenomena, and unexplained patterns emerge from the darkness, each one a puzzle, each one a mystery waiting to be solved. From black holes that twist space and time to galaxies that seem to break the rules of physics, these anomalies challenge our very understanding of reality. They are the outliers, the unexplainable forces that leave scientists awestruck and humanity humbled. Tonight, we embark on a journey across the stars to uncover these extraordinary phenomena. Let us begin. Our exploration begins with one of the most terrifying and fascinating space anomalies ever discovered, the black hole. A black hole is not merely a region of empty space, but a cosmic trap where gravity becomes so overwhelming that nothing, not even light, can escape. These invisible giants are born from the collapse of massive stars, and their existence warps the very fabric of reality. Surrounding many black holes lies the accretion disk, a searing halo of gas and dust spiraling inward, glowing brighter than entire galaxies as it's consumed. But even more perplexing is the event horizon, the boundary beyond which all information vanishes. To us, anything crossing this threshold is lost forever, locked away in an eternal void. Yet, questions remain. What happens to matter once it falls in? Does it cease to exist, or is it transformed into something new, hidden in the depths of an unknowable singularity? Some black holes defy explanation altogether. Take the example of ultramassive black holes, millions, even billions of times heavier than our Sun. How could such monstrosities form so quickly after the Big Bang? Their existence suggests that the early universe may have produced them through unknown mechanisms, perhaps involving dense clouds of primordial gas collapsing directly into black holes. And then there are rogue black holes, drifting silently between the stars. Invisible and deadly, they carry no bright disks to warn us of their approach, yet their gravitational influence distorts everything around them. What makes black holes especially anomalous is that they force physics into a corner. General relativity describes their gravity, but quantum mechanics suggests information cannot simply disappear. Somewhere in this paradox lies a deeper truth, one that remains hidden in the shadows of these cosmic enigmas. From the crushing depths of black holes, we move to another class of extraordinary objects, neutron stars. These are the remnants of massive stars that have exploded in supernovae, leaving behind cores so dense that a teaspoon of their material would weigh billions of tons on Earth. Neutron stars push matter to its absolute limits, compressing atomic nuclei into a state we cannot replicate in any laboratory. They are often only about 20 kilometers across, yet they can contain more mass than our Sun. Among neutron stars, some exhibit behavior so extreme they verge on the unimaginable. Pulsars, for example, emit beams of electromagnetic radiation that sweep across the cosmos like cosmic lighthouses. They rotate with staggering precision, some spinning hundreds of times per second. These pulses are so regular that scientists once considered them potential signals from alien civilizations. In fact, the first pulsar ever detected was labeled LGM-1 for Little Green Men, before researchers confirmed its natural origin. Yet neutron stars are not always stable. Some transform into magnetars, the most magnetic objects known in the universe. Their magnetic fields are trillions of times stronger than Earth's, powerful enough to distort atomic structures and release bursts of energy that can outshine entire galaxies for brief moments. These gamma-ray flares, unleashed without warning, demonstrate just how violent and unpredictable these stellar corpses can be. Even stranger are binary systems where a neutron star orbits closely with another star. In such pairs, the neutron star can siphon material from its companion, creating bursts of X-rays as the matter collides with its surface. Sometimes, the orbiting stars spiral together, merging in spectacular kilonova explosions that forge heavy elements like gold and platinum, cosmic alchemy on the grandest scale. The study of neutron stars reveals that the universe does not simply end with death, it reshapes itself into exotic new forms. These remnants are not mere anomalies. They are keys to unlocking the physics of matter under conditions we can barely comprehend, windows into a realm where nature itself seems to bend the rules. Leaving neutron stars behind, our attention shifts to the quasars, the cosmic beacons of the early universe. Quasars are powered by supermassive black holes at the centers of young galaxies. As matter spirals into their hungry maws, it heats up to unimaginable temperatures, emitting light so intense it can outshine the combined stars of hundreds of galaxies. Some quasars are located billions of light-years away, yet they still appear bright to our telescopes, proof of their staggering luminosity. What makes quasars such anomalies is not just their brilliance, but their age. Many quasars we detect formed less than 1 billion years after the Big Bang, far earlier than we would expect such colossal black holes to exist. How could the universe, so young and still forming its first stars, already harbor these titans? This mystery suggests that black holes may have grown much faster than current models allow, or that they formed through mechanisms still unknown, perhaps direct collapses of primordial gas clouds into massive black holes without passing through the usual stellar stage. Quasars also act as cosmic lighthouses in another sense. Their radiation illuminates the intergalactic medium, allowing astronomers to study the invisible gas and dark matter web connecting galaxies. Through them, we glimpse the large-scale structure of the universe. They are not only anomalies in their own right but also tools that reveal the hidden skeleton of the cosmos. And then there are the enigmatic blazars, quasars that emit jets of plasma pointed almost directly at Earth. Their light flickers and flares unpredictably, as though signaling across unimaginable distances. They remind us that even phenomena we think we understand can shift into stranger, more extreme manifestations, keeping the universe one step ahead of our comprehension. If quasars are the cosmic lanterns, then cosmic voids are their shadows. Voids are vast, empty regions of the universe, stretching hundreds of millions of light-years across with scarcely a galaxy inside. They represent the great absences of the cosmos, where matter is so sparse that it challenges our understanding of how the universe organizes itself. These regions are not mere gaps, they are anomalies in the very structure of the cosmos. Our universe is arranged in a cosmic web, where galaxies cluster along filaments of dark matter and gas. Between these filaments lie the voids, immense bubbles of near-nothingness. Within them, galaxies are rare and lonely, often small and faint, their growth stunted by isolation. To float in the heart of a void would be to see only a handful of galaxies scattered faintly across the sky, a stark contrast to the dense clusters seen elsewhere. One of the greatest mysteries is why voids are so empty. Simulations suggest some matter should still drift through them, but observations reveal even less than expected. Could dark energy, the mysterious force driving cosmic expansion, be thinning these regions faster than we predict? Or might voids be windows into something deeper, places where the familiar rules of physics fray at the edges? There is also speculation that cosmic voids may amplify signals of the universe's underlying geometry. By studying how light passes through these emptinesses, we may one day determine whether space is truly uniform or subtly curved on unimaginable scales. Paradoxically, by staring into nothing, we may uncover everything. From emptiness, we turn to one of the strangest inhabitants of our galaxy, the rogue planets. Unlike Earth, which orbits the steady warmth of the Sun, rogue planets wander through interstellar space without a parent star. They drift silently, frozen and dark, invisible against the cosmic backdrop unless revealed by chance. Their existence challenges our assumptions of planetary systems as ordered families orbiting stars. Astronomers estimate there may be billions of these nomadic worlds in our galaxy alone, perhaps even more numerous than stars themselves. Some are thought to have been ejected from their original systems by gravitational chaos, flung into the void during the turbulent early days of planetary formation. Others might have formed directly in isolation, miniature worlds born in the cold darkness of interstellar clouds. What makes rogue planets so anomalous is the question of whether they could still harbor life. Without a star, they lack sunlight, but heat may come from within. A thick atmosphere or insulating ice shell could trap geothermal energy, maintaining subsurface oceans. In theory, microbial life could thrive beneath frozen crusts, surviving in eternal night. If so, the galaxy may be teeming with hidden biospheres, traveling unseen between the stars. Detecting these wanderers is an enormous challenge. Without stellar light to reflect, they are nearly invisible, spotted only through rare gravitational lensing events when they pass in front of background stars. Each detection is like catching a ghost in the act, fleeting and precious. These dark, drifting planets remind us that the familiar order of solar systems is only part of the story, that the universe holds worlds we may never see, but which still shape its vast narrative. One of the most extraordinary anomalies in the universe is the presence of gravitational waves, ripples in the very fabric of space-time itself. Predicted long ago but only directly detected in recent years, these waves are created by some of the most violent events imaginable: colliding black holes, merging neutron stars, and even the birth of the universe itself. Unlike light, gravitational waves do not scatter as they travel. They carry unaltered information across billions of light-years, acting as messengers from the most extreme corners of reality. The anomaly lies not in their existence, but in the staggering energies they represent. When two black holes spiral into each other, they release more power in a fraction of a second than all the stars in the observable universe combined. Yet the waves we measure on Earth distort space by less than the width of a proton. Detecting them requires instruments of unimaginable sensitivity, vast laser interferometers stretching kilometers in length, capable of recording distortions so tiny they border on impossible. But the implications are even stranger. By listening to gravitational waves, astronomers can now study cosmic events invisible to telescopes. Black hole collisions, hidden in darkness, suddenly become detectable. Neutron-star mergers not only produce waves but also forge heavy elements, linking physics, chemistry, and astronomy in one violent act. Some speculate that by studying these waves, we might one day peer further back in time than light itself allows. If we can detect the faint background hum of gravitational waves from the Big Bang, we will hold in our hands a direct echo of creation, a cosmic signature unlike anything else. If gravitational waves are the whispers of the cosmos, then gamma-ray bursts are its deafening roars. These brief, powerful explosions are among the most energetic events known, releasing more energy in seconds than our sun will emit in its entire lifetime. They arrive as sudden flashes of high-energy radiation, often lasting mere seconds, yet their brilliance can outshine entire galaxies across the universe. Gamma-ray bursts come in two main types, long and short. Long bursts are thought to occur when massive stars collapse into black holes, while short bursts result from merging neutron stars. Both are violent, catastrophic events, but their details remain puzzling. How can such compact regions of space unleash such ferocity? Even more mysterious are the afterglows, trails of radiation that persist after the initial burst, stretching across the electromagnetic spectrum from X-rays to radio waves. These afterglows allow astronomers to trace the bursts back to distant galaxies, some billions of light-years away. They reveal that gamma-ray bursts are not rare but rather sprinkled throughout the universe, occurring regularly yet unpredictably. For planets unfortunate enough to be near one, the consequences are catastrophic. A nearby gamma-ray burst could strip away an atmosphere, sterilizing a world in moments. Some scientists even speculate that mass extinctions in Earth's history may have been triggered by such blasts, distant but devastating. Yet these cosmic anomalies may also be creative. By seeding space with heavy elements forged in the explosions, gamma-ray bursts play a role in enriching the universe, ensuring that future generations of stars and planets have the ingredients for complexity and life. In their fury lies the blueprint for creation. As we continue deeper into the unknown, we encounter an anomaly that permeates everything yet remains invisible: dark matter. For decades, astronomers have observed galaxies spinning in ways that defy Newtonian expectations. Stars at the edges of galaxies move far too quickly to be held by the gravity of visible matter alone. The explanation: an unseen form of mass, outweighing all the stars and planets combined, silently shaping the cosmos. Dark matter makes up about 27% of the universe, yet no telescope can see it. It does not emit, absorb, or reflect light. We know it only through its gravitational effects, how it bends light through lensing, how it anchors galaxies within clusters, and how it influences the large-scale structure of the cosmic web. Without it, galaxies would fly apart, unable to hold themselves together. But what is it? That remains one of the greatest anomalies in science. Some theories suggest it could be made of exotic particles yet to be discovered, such as WIMPs or actions. Others propose more radical ideas, that dark matter might represent entire hidden sectors of physics, perhaps even mirror universes intertwined with our own. What deepens the mystery is its distribution. Dark matter forms vast halos around galaxies, invisible cocoons that dictate their behavior. These halos extend far beyond the visible edges of galaxies, hinting that what we see is only the tip of an immense, hidden iceberg. The search for dark matter continues with underground detectors, particle accelerators, and astronomical surveys. Each failed detection only amplifies the anomaly, reminding us that the universe is built upon foundations we cannot yet see, let alone understand. If dark matter is the invisible scaffold of the universe, then dark energy is the hidden hand pushing it apart. In the late 20th century, astronomers studying distant supernovae expected to find that the expansion of the universe was slowing down under the pull of gravity. Instead, they uncovered a stunning anomaly: the expansion is accelerating. Something unknown is driving galaxies away from each other faster and faster, and that mysterious force is what we now call dark energy. Unlike dark matter, which clumps and gathers around galaxies, dark energy seems to be smooth, filling space uniformly. It makes up nearly 70% of the universe, dominating its fate, yet we have no clear idea what it actually is. Some scientists suggest it might be a property of space itself, a cosmological constant woven into the fabric of reality. Others speculate that it could be the manifestation of a new, exotic field permeating the cosmos, or even evidence of hidden dimensions. The strangest part of this anomaly is its implication for the future. If dark energy continues to accelerate expansion unchecked, galaxies will drift farther apart until their light no longer reaches us. In trillions of years, the night sky could go dark, leaving future observers in isolation, unaware of the universe beyond their own galaxy. Some scenarios even predict a big rip, where acceleration grows so violent that galaxies, stars, planets, and eventually atoms themselves are torn apart by the stretching of space. Dark energy is perhaps the greatest riddle in modern science, an unseen force not only shaping the universe but determining how it will end. While dark matter and dark energy challenge our understanding of the cosmos at large, another anomaly lurks closer to home: fast radio bursts, FRBs. These are sudden, intense flashes of radio waves that last only milliseconds, yet in that brief time release more energy than our sun produces in days. First discovered in 2007, they have since become one of the most intriguing mysteries in astronomy. What causes them? That question remains open. Some FRBs appear to originate from distant galaxies billions of light-years away, meaning their power is unimaginable. Others repeat, flashing again and again from the same region, while many are one-time events, vanishing forever after their brief appearance. The leading theories involve neutron stars and magnetars. A sudden quake in a magnetar's crust could unleash a burst of radio energy detectable across the universe. But the repeating nature of some FRBs doesn't fully fit this model. Other explanations range from black hole activity to collisions of exotic objects. And then there are the wilder speculations. Because FRBs are so precise and powerful, some have wondered whether they could be artificial signals, perhaps leakage from advanced alien technology, or even deliberate attempts at interstellar communication. While natural explanations remain more likely, the possibility that these signals carry more than just random bursts keeps imaginations alive. Every new detection adds to the puzzle. With radio telescopes now scanning the skies continuously, FRBs have gone from rare anomalies to frequent mysteries, each one a reminder that the universe still speaks in languages we have only just begun to decode. From fleeting signals to colossal structures, the universe presents anomalies on scales so vast they boggle the mind. One of these is the discovery of giant cosmic structures. Arrangements of galaxies stretching billions of light-years, far larger than what our models predict should exist. The universe is supposed to be uniform on the largest scales. According to the cosmological principle, matter should be distributed evenly when viewed from far enough away. Yet surveys have uncovered colossal structures that defy this expectation. The Sloan Great Wall, for example, is a filament of galaxies nearly 1.4 billion light-years long. Even larger is the Hercules Corona Borealis Great Wall, spanning over 10 billion light-years, an anomaly so vast that it challenges the very foundations of cosmology. How could such immense structures form in the limited time since the Big Bang? Gravity, while powerful, works slowly. The existence of these walls and filaments suggests that matter may have been influenced by forces beyond the standard model of cosmology. Some scientists argue that such discoveries may simply be statistical outliers. Others wonder if they hint at physics beyond our current theories, or even connections between regions of space we thought were independent. These structures are not just scientific curiosities, they redefine our sense of scale. If galaxies are like islands, then these cosmic walls are continents, rewriting our map of the universe. Their existence forces us to confront the possibility that the cosmos is stranger, larger, and more interconnected than we ever imagined. Among the strangest celestial objects ever proposed are the theoretical white holes. If black holes are regions where matter and light are trapped forever, white holes are their hypothetical opposites, regions from which nothing can enter, only escape. In theory, a white hole would spew matter and energy outward, a fountain of creation rather than destruction. White holes arise naturally in the equations of general relativity, but so far none have been observed. Their existence would upend our understanding of the universe. Could they be the other end of a black hole, connected through a wormhole or Einstein-Rosen bridge? Some models suggest that matter falling into a black hole might one day emerge from a white hole in another part of the cosmos, or even in another universe altogether. But problems remain. White holes would appear unstable, any disturbance might cause them to collapse instantly. Still, their mystery keeps them alive in theoretical physics. Some researchers speculate that the Big Bang itself could have been a kind of white hole, an eruption of energy and matter into our universe from some deeper, unknown reality. Even without direct evidence, the concept of white holes pushes us to question the boundaries of space and time. They stand as a reminder that our theories may describe not only what we see, but also what might exist beyond our current reach, waiting for discovery. Another anomaly that fascinates both scientists and dreamers is the possibility of wormholes, tunnels through space-time connecting distant regions of the universe. Predicted as mathematical solutions to Einstein's equations, wormholes, or Einstein-Rosen bridges, could, in theory, allow faster-than-light travel by bypassing the normal fabric of space. The idea is captivating. A spacecraft could enter a wormhole near Earth and emerge light-years away in moments. Such passages could even connect entirely different universes. But the reality is far less certain. Wormholes, if they exist, would require exotic forms of matter with negative energy density to remain stable. Without it, they would collapse instantly. Despite these challenges, wormholes continue to intrigue researchers because they provide a window into physics beyond what we know. They also appear in discussions of quantum mechanics and black hole information paradoxes, suggesting possible links between the smallest and largest scales of reality. Even if stable wormholes never exist, the mere possibility forces us to imagine the cosmos not as a vast, empty expanse but as a web of hidden shortcuts and connections. They may remain in the realm of theory for now, but their presence in our equations hints that the universe may have layers of complexity we have barely begun to comprehend. Beyond wormholes lies another cosmic anomaly, time distortions caused by extreme gravity. According to relativity, time does not flow at a universal rate. Instead, it bends and stretches depending on gravity and motion. Near a massive object like a black hole, time slows relative to an observer far away. This is not science fiction, it is measurable fact. Experiments with satellites and atomic clocks confirm that time passes differently in orbit compared to on Earth. For spacecraft near Jupiter, or for astronauts traveling at high speeds, time ticks slightly slower. On human scales, the difference is tiny. But near black holes, it becomes dramatic. Imagine an explorer approaching the event horizon of a black hole. To them, moments pass normally. But to distant observers, their time slows, appearing almost frozen as they near the horizon. In extreme cases, billions of years could pass in the universe outside while only hours unfold for the traveler. This distortion raises profound questions. Could advanced civilizations harness such effects, stretching their lifespans relative to the universe? Could the future itself already exist, waiting for those who venture into these regions? Time, which we often think of as absolute, is revealed as flexible, an illusion shaped by the cosmos itself. In this way, anomalies in time are not just curiosities, they reshape our very concept of reality. The universe is not a stage upon which time unfolds. Instead, time is woven into the stage itself, twisted and bent by gravity, leaving us to question what is truly real. Among the most powerful cosmic phenomena ever witnessed are supernovae, the explosive deaths of massive stars. When a star many times heavier than our Sun exhausts its nuclear fuel, gravity wins the eternal battle, crushing the core until it rebounds in a cataclysmic blast. In a moment, the star releases more energy than it produced during its entire lifetime. Supernovae are not just spectacular light shows, they are engines of creation. Elements heavier than iron, gold, silver, uranium are forged in their fiery crucibles and hurled into space. Without these explosions, planets like Earth, and even life itself, could not exist. Every atom of calcium in our bones and iron in our blood was once born in the heart of a dying star. Yet not all supernovae behave as expected. Some defy classification, burning brighter or lasting longer than models predict. These superluminous supernovae shine dozens of times more intensely than typical ones, leaving astronomers to wonder what fuels such extreme power. Could they be driven by hidden magnetars, spinning rapidly and injecting energy into the explosion? Or are they triggered by stars so massive they collapse in ways never before seen? Supernovae are also cosmic milestones, marking the transition from one stellar generation to the next. They are both destroyers and creators, anomalies of violence that paradoxically give rise to beauty. In every galaxy, their echoes remind us that endings in the cosmos are never truly final. Beyond even the most violent supernovae lies an even rarer phenomenon, the hypernova. These titanic explosions occur when exceptionally massive stars collapse, producing gamma-ray bursts alongside their destruction. A hypernova can unleash 10 times the energy of a typical supernova, turning a single star into one of the brightest events in the universe. Hypernovae push our understanding of stellar death to its limits. They are thought to arise from stars more than 30 times the mass of the Sun, collapsing directly into black holes while spewing out relativistic jets of energy. These jets, aimed in narrow beams, can cut across galaxies, their radiation piercing space for billions of light years. Such events are rare, but their impact is immense. They can sterilize nearby star systems, alter galactic environments, and seed the cosmos with vast amounts of heavy elements. The energy released is so great that, for a brief moment, a hypernova rivals the brightness of the entire observable universe. What remains puzzling is their unpredictability. We can identify stars that might end in hypernovae, but the precise triggers remain elusive. The balance between mass, rotation, and magnetic fields plays a role, but the exact recipe is a cosmic secret. Each hypernova detected challenges our models, reminding us that even the most extreme theories may fall short when faced with reality. While hypernovae mark dramatic endings, other anomalies reveal hidden beginnings, the mystery of cosmic microwave background, CMB, anomalies. The CMB is the faint afterglow of the Big Bang, radiation left over from when the universe was only 380,000 years old. It should be nearly uniform, a smooth bath of microwaves spread evenly across the sky. Yet, detailed maps reveal subtle irregularities. One such irregularity is the so-called cold spot, a region of the sky where the CMB is unexpectedly cooler than surrounding areas. Some scientists suggest it may simply be a statistical fluke. Others propose more exotic explanations. Perhaps it is caused by a massive void in the universe, or even a sign of interaction with another universe beyond our own. Another anomaly is the unexpected alignment of large-scale CMB patterns, dubbed the axis of evil. These alignments seem to defy the assumption that the universe should look the same in all directions. Are they the result of measurement errors, or do they hint at something deeper, an imprint of physics we do not yet understand? The CMB is our most direct window into the early universe, yet its anomalies remind us that even our origin story is filled with unresolved puzzles. Each irregularity whispers that the cosmos may be stranger than our theories allow, and that the very birth of reality still hides secrets waiting to be uncovered. From the faint afterglow of creation, we now turn to a mystery much closer yet equally perplexing, Oumuamua, the first known interstellar object to pass through our solar system. Discovered in 2017, this elongated body tumbled through space at incredible speed, unlike anything seen before. Its trajectory revealed that it came from outside the solar system, a visitor from the stars. What baffled scientists was not just its origin, but its behavior. Oumuamua accelerated slightly as it moved away from the Sun, but without the usual signs of outgassing seen in comets. No visible tail, no jets of dust or ice, just a silent, unexplainable push. Its shape also appeared unusual, possibly cigar-like or pancake flat, adding to the mystery. The anomaly sparked a storm of theories. Some proposed that Oumuamua was a fragment of a shattered planet, ejected from another star system. Others suggested it might be composed of exotic hydrogen ice that evaporates invisibly. And then there were the bold speculations that it could be an artificial object, perhaps a probe or fragment of alien technology, drifting silently through interstellar space. Though Oumuamua has now faded beyond our reach, its brief passage was enough to ignite debate and inspire new missions designed to intercept future interstellar visitors. Whatever it truly was, Oumuamua reminded us that the solar system is not isolated, it is part of a vast galactic sea, and sometimes, mysterious travelers cross our path. As if one interstellar visitor were not enough, another anomaly soon followed, two-eyed Borisov, discovered in 2019. Unlike Oumuamua, this object appeared more familiar. It had a clear cometary tail, venting gas and dust as it approached the Sun. Yet what made Borisov extraordinary was its unmistakable origin beyond our solar system. For the first time, humanity had the chance to study an interstellar comet up close. Its composition, surprisingly, was not too different from comets in our own system, suggesting that the processes forming icy bodies may be universal across the galaxy. But subtle differences hinted at alien chemistry, slightly unusual ratios of carbon monoxide and other molecules. The existence of Borisov, following Oumuamua so soon, implied that interstellar objects may not be as rare as once thought. Perhaps countless such wanderers drift between the stars, remnants of planetary systems disrupted long ago. If so, the Milky Way may be filled with fragments of other worlds, carrying clues to their histories. Borisov also sparked deeper questions. Could such interstellar bodies serve as natural messengers, spreading organic molecules or even microbial life between star systems? This idea, known as panspermia, suggests that life might not be confined to its world of origin but could travel on icy comets across the galaxy. Seen this way, interstellar visitors are not just anomalies, they may be part of a grand cosmic exchange, a mechanism by which the universe seeds itself with the potential for life. From interstellar wanderers, we return to the heart of our own galaxy, where another anomaly reigns, Sagittarius A*, the supermassive black hole at the center of the Milky Way. Measuring over 4 million times the mass of the Sun, it is cloaked in mystery and hidden behind clouds of gas and dust. For decades, astronomers suspected its presence by tracking the orbits of stars whipping around an invisible point with incredible speed. Their motion could only be explained by the gravity of a colossal, compact object. In 2022, the Event Horizon Telescope collaboration finally unveiled the first image of Sagittarius A*, revealing a glowing ring of gas surrounding its shadow. Yet questions remain. How did such a massive black hole form in the center of a relatively ordinary galaxy? And why does it flare unpredictably, releasing bursts of energy from materials swirling near its horizon? Unlike the monstrous quasars in distant galaxies, Sagittarius A* is relatively quiet, a sleeping giant. But at times, it awakens, flickering with X-rays as if stirred from its slumber. Some researchers even wonder whether supermassive black holes like Sagittarius A* play a crucial role in galactic evolution, regulating star formation through their outbursts. Far from being passive anomalies, they may act as engines shaping the destiny of galaxies themselves. For us, Sagittarius A* is both a cosmic anomaly and a neighbor, a reminder that even in our galactic home, mysteries lurk at the very heart of existence. While Sagittarius A* commands the heart of our galaxy, there are even stranger anomalies in the cosmic zoo, binary black hole systems. Instead of a single black hole devouring its surroundings, these come in pairs, locked in a gravitational dance. As they orbit each other, they generate enormous distortions in space-time, releasing waves that ripple outward across the universe. The most famous detection of such a merger came in 2015, when LIGO first recorded the faint tremor of colliding black holes. Two objects, each tens of times the mass of the Sun, spiraled together in their final seconds, converting a portion of their mass directly into gravitational energy. The signal, lasting just fractions of a second, confirmed Einstein's predictions and opened an entirely new way of observing the universe. But anomalies remain. Some black holes in binary systems appear far heavier than expected, challenging models of how massive stars evolve. Others merge more frequently than anticipated, hinting at environments, perhaps dense star clusters, where such systems form more easily. Even more tantalizing are the prospects of supermassive binary black holes, pairs of giants millions of times the Sun's mass orbiting one another at galactic centers. Their eventual collisions would unleash gravitational waves of staggering magnitude, detectable across cosmic distances. Yet despite decades of searching, clear evidence of such mergers remains elusive. These systems are reminders that black holes are not static anomalies but dynamic participants in the cosmic story, shaping galaxies, generating waves, and forcing us to rethink how matter, energy, and space-time itself evolve. Beyond the centers of galaxies lies another cosmic puzzle: rogue stars. Unlike most stars, which reside within stable galactic orbits, rogue stars are ejected into intergalactic space, drifting alone in the void. How do such stellar exiles come to be? The answers lie in violent gravitational interactions. When galaxies collide, their stars usually pass harmlessly by one another. But in regions near supermassive black holes or dense star clusters, chaotic encounters can slingshot stars to incredible velocities, ejecting them beyond the gravitational pull of their home galaxies. These hypervelocity stars streak through the cosmos at millions of kilometers per hour, bound for intergalactic emptiness. The anomaly of rogue stars lies in their isolation. Without the gravitational embrace of a galaxy, their futures are cold and lonely. Yet, they may carry planetary systems with them, dragging entire miniature worlds into the void. Could life exist on planets orbiting a star exile between galaxies, with no nearby suns in sight? The thought borders on science fiction, yet physics places no firm prohibition. Astronomers have begun detecting more of these wanderers, their speeds betraying their violent origins. Each rogue star is a story of cosmic chaos, a reminder that galaxies are not static islands but dynamic arenas where gravity constantly reshuffles the players. Among the most haunting anomalies in astrophysics are black hole jets, colossal streams of energy and matter launched from regions near black holes at nearly the speed of light. Strangely, though nothing can escape a black hole itself, these jets emerge from the swirling chaos just outside the event horizon, extending for thousands or even millions of light-years. The mechanisms behind these jets remain mysterious. Magnetic fields are thought to play a role, channeling matter from the accretion disk into narrow beams. But why some black holes generate such immense jets while others remain silent is unknown. These jets are so powerful that they can shape entire galaxies, heating gas, halting star formation, and even blowing matter into intergalactic space. Seen through telescopes, they are among the most spectacular sights in the cosmos, thin, bright lances of energy stretching across space, dwarfing the galaxies that birthed them. Some jets end in glowing lobes, where their energy collides with intergalactic matter, creating massive radio structures larger than hundreds of galaxies combined. The anomaly deepens when we consider their scale. How can something so small, an event horizon measured in kilometers, power structures millions of light-years long? The gap between cause and effect is staggering, suggesting processes we only partly understand. Black hole jets remind us that even in regions defined by destruction, the universe creates phenomena of stunning complexity, light born in darkness, order emerging from chaos. If black hole jets are colossal engines of energy, then quark stars represent the tiniest yet strangest anomalies of matter. These hypothetical objects might form when neutron stars collapse even further under extreme pressure, squeezing particles into their most fundamental components, quarks. Instead of being composed of neutrons packed tightly together, a quark star would be a sea of free-floating quarks, bound only by the most fundamental forces of nature. So far, no quark star has been confirmed, but hints have emerged. Some pulsars exhibit unusual properties, such as unexpected brightness or strange rotational patterns, that don't quite fit with conventional neutron star models. Could these anomalies point to an entirely new state of matter? If confirmed, quark stars would not just be rare curiosities, they would expand our knowledge of how matter behaves at the highest densities imaginable. Quark stars also inspire more exotic theories. Some researchers speculate about strange quark matter, a form that could be more stable than ordinary atomic matter. If such matter exists, it might transform normal matter upon contact, spreading like a chain reaction. Thankfully, this remains theoretical, but it underscores how little we truly know about the boundaries of matter and energy. In the cosmic hierarchy, quark stars sit on the thin line between what we can observe and what we can only imagine. If discovered, they would stand as monuments to nature's ability to sculpt anomalies stranger than our boldest theories. As strange as quark stars may be, another anomaly challenges the very concept of what a star can be, the Thorne-Asitko object, TO. This exotic star is believed to form when a neutron star sinks into the core of a red supergiant. Instead of being consumed, the neutron star becomes enveloped, orbiting inside the larger star's body, hidden beneath layers of gas and plasma. The result is a bizarre hybrid. A star within a star. On the outside, a TO resembles an ordinary red supergiant, glowing brightly in the night sky. But inside, its core is unlike anything else, a neutron star embedded within stellar material, creating unique nuclear reactions that cannot occur in normal stars. Evidence for TZOs remains sparse, but astronomers have identified a handful of red supergiants with chemical signatures that suggest they may harbor neutron star cores. If confirmed, they would be one of the rarest types of stars in the universe, living anomalies that bridge two stellar categories once thought separate. The existence of TZOs demonstrates that cosmic collisions do not always destroy, they sometimes merge in ways that create new and unexpected forms. It is a reminder that the line between stability and catastrophe in the universe is thin, and often, it leads to discoveries that defy classification. From stellar hybrids, we move to anomalies on the largest possible scales. The cosmic expansion itself. For decades, astronomers have measured the rate at which the universe expands, defined by the Hubble constant. But here lies one of modern cosmology's greatest puzzles: different methods yield conflicting results. When astronomers measure expansion by observing nearby galaxies and supernovae, they arrive at one value for the Hubble constant. Yet when they use the cosmic microwave background to calculate expansion, they get a slightly lower value. Both methods are precise, both are grounded in solid physics, yet they disagree. This discrepancy is known as the Hubble tension, and it may point to something profound. Perhaps new forms of physics are at play, undiscovered particles influencing the early universe, or subtle interactions in dark matter and dark energy that our models don't capture. Some suggest modifications to the theory of gravity itself, or even the possibility that our understanding of cosmic expansion is incomplete. The Hubble tension reminds us that anomalies are not always rare, distant events. Sometimes, they lie in the very numbers we use to describe reality. Hidden within the equations may be the seeds of a scientific revolution, one that forces us to rethink not just how the universe grows, but why. Not all anomalies are found in the distant reaches of the cosmos, some arise in the very heart of planetary systems. One such mystery lies in the discovery of hot Jupiters, giant gas planets orbiting their stars at distances so close that a year lasts only a few days. When exoplanets were first detected, astronomers expected to find systems resembling our own, rocky inner worlds, giant planets farther out. Instead, they encountered these massive gas giants hugging their stars so tightly that their atmospheres boil away into space. The anomaly is how they came to be. Giant planets are thought to form in the colder, outer regions of protoplanetary disks, where ice and gas can accumulate. How then do we explain worlds the size of Jupiter orbiting so close to their suns? The prevailing idea is that they formed far away and migrated inward, dragged by gravitational interactions with disks or other planets. But the process is poorly understood, and many hot Jupiters defy even these models. Their atmospheres also pose puzzles. Some glow with unexpected colors, some appear puffed up as though inflated, and others show traces of exotic molecules not predicted by theory. Observing them pushes the limits of our telescopes, yet each new discovery expands our understanding of what planets can be. Hot Jupiters remind us that our solar system may not be the template for all planetary systems, it may itself be the anomaly, a quiet outlier in a universe filled with stranger worlds. Moving from planetary anomalies to galactic ones, we encounter galaxies without dark matter, or at least galaxies that appear to lack it. In 2018, astronomers announced the discovery of a faint galaxy known as NGC 1052 or DF2. Unlike other galaxies, its stars move in ways that suggest little to no invisible mass is holding it together. This finding was shocking. For decades, dark matter has been the key to explaining how galaxies form and remain stable. Without it, stars should simply drift apart. Yet here was a galaxy that seemed to defy the rule, existing without the hidden scaffolding of dark matter. Some argued that perhaps the galaxy was mismeasured, that its distance or brightness had been misunderstood. Others suggested that interactions with nearby galaxies stripped away its dark matter halo, leaving behind a visible skeleton. Yet additional discoveries of similar galaxies reinforce the anomaly. Dark matter might not be as universally distributed as once believed. If confirmed, these galaxies could force us to refine our understanding of how dark matter works. Or even whether alternative explanations, like modifications to gravity, might be at play. They challenge the notion that one theory can fit all, reminding us that the universe often makes exceptions to its own rules. On an even grander scale, we face the puzzle of galaxies that spin too fast or too slow for their size. While dark matter explains many rotation curves, anomalies persist. Some dwarf galaxies, for instance, spin much faster than expected given their visible matter, even with dark matter models applied. Others seem to rotate unusually slowly, as if missing the invisible glue that should hold them together. These discrepancies have sparked debate. Do we misunderstand the nature of dark matter? Or are these galaxies evidence of alternative physics, such as modifications to the law of gravity at very low accelerations? The idea, known as modified Newtonian dynamics, suggests that gravity itself might behave differently on galactic scales. Though controversial, MOND fits some of these anomalous galaxies better than dark matter models. Yet it struggles to explain the broader universe as effectively as the dark matter paradigm. The tension between these explanations highlights the uncertainty in our models. Perhaps both are partly true, or perhaps a deeper, unified theory awaits discovery. Each galaxy that spins wrong becomes a cosmic protest against simplicity. They remind us that the universe does not bow to our expectations, but instead challenges us to adapt our theories to match its strange, often contradictory reality. One of the strangest cosmic puzzles lies not in stars or galaxies, but in the Great Attractor, a mysterious gravitational anomaly pulling our galaxy, along with thousands of others, toward a region of space we cannot fully see. Discovered in the 1970s, the Great Attractor lies in the direction of the Centaurus constellation, hidden behind the thick plain of the Milky Way. The anomaly is not merely a cluster of galaxies, it appears to be something far larger, a region of immense mass bending the motions of entire galactic superclusters. The Milky Way, the Andromeda Galaxy, and countless others are all drifting toward it at over 600 kilometers per second. Yet because it lies in the so-called zone of avoidance, obscured by dust and stars, direct observation is difficult. Some studies suggest the Great Attractor is part of the Laniakea supercluster, an immense web of galaxies stretching across hundreds of millions of light-years. Others hint that the anomaly may represent something deeper, perhaps an unusually dense concentration of dark matter or a hidden structure beyond current maps of the cosmos. Whatever it is, the Great Attractor reminds us that we are not stationary in the universe. The Milky Way itself is on a one-way journey, pulled inexorably toward a gravitational destiny hidden in the shadows. If the Great Attractor unsettles with its hidden pull, then Hoag's object confounds with its beauty. This rare galaxy appears as a perfect ring, a glowing circle of young, blue stars surrounding a bright, yellow core. Discovered in 1950, it defies the normal classifications of galaxies, which usually take on spiral, elliptical, or irregular shapes. Ring galaxies are rare, and Hoag's object is the most striking example. Its symmetry is uncanny, as though sculpted with precision. Astronomers debate how it formed. Some propose a collision with another galaxy long ago, which triggered waves of star formation that expanded outward into a ring. Others suggest internal gravitational instabilities might have reorganized its structure. Yet no explanation fully accounts for its perfection. Adding to the enigma, nestled in the background behind Hoag's object is another, smaller ring galaxy, eerily similar in appearance. This cosmic coincidence fuels speculation. Are ring galaxies more common than we think, or are we simply fortunate to witness such rare alignments? Hoag's object is not just an anomaly in form, it is a reminder that the universe is capable of creating structures of astonishing symmetry and elegance, rivaling even the most intricate human designs. From graceful rings to terrifying enigmas, we confront the puzzle of dark galaxies, galactic structures composed almost entirely of dark matter, with little to no stars to illuminate them. Their existence was long theorized, but only recently have astronomers begun finding candidates through gravitational lensing and hydrogen gas mapping. Unlike ordinary galaxies, dark galaxies are nearly invisible, betraying their presence only by the way they bend light or the faint radio emissions of their gas. Some appear to contain the mass of billions of stars, yet produce no light at all. Why do they exist? Why did their gas fail to ignite into shining stars? One possibility is that conditions in these galaxies prevented cooling, stopping gas clouds from collapsing into stars. Another is that early supernovae expelled much of their material before stars could form. Whatever the reason, they challenge our definitions. What is a galaxy if it has no light? Dark galaxies are the ghosts of the cosmos, unseen but influential. They may outnumber luminous galaxies, silently shaping the web of the universe. If true, then much of the structure of the cosmos is hidden from view, waiting for instruments sensitive enough to expose its shadowy skeleton. Among the strangest discoveries in recent decades are the taboo regions of galactic rotation curves, areas where stars and gas seem to move in ways that defy both dark matter models and modified gravity theories. These anomalies are particularly striking in ultra-diffuse galaxies, where stars are so spread out that the galaxy resembles a faint ghost drifting through the void. In some cases, these galaxies rotate far faster than their meager mass should allow. In others, they move sluggishly, as though missing the dark matter that should keep them intact. Each new observation seems to raise as many questions as it answers. Are these outliers evidence of unique galactic histories, shaped by collisions or tidal stripping? Or do they signal flaws in our most fundamental models of cosmic structure? One particularly puzzling ultra-diffuse galaxy, Dragonfly 44, was once thought to be 99% dark matter, yet subsequent measurements cast doubt, suggesting its nature may be far stranger. Such objects lie at the edge of our understanding, anomalies that test the limits of both observation and theory. They are reminders that galaxies, far from being uniform building blocks, are as diverse and unpredictable as snowflakes, each one shaped by forces we may not yet comprehend. Venturing closer to home, we encounter another anomaly, the peculiar tilt of our solar system. The orbits of planets around the Sun are remarkably aligned, lying within a flat disk called the ecliptic. Yet this plane is tilted by about 6 degrees relative to the Sun's equator. Why should the solar system's architecture be slightly askew? Some theories suggest that interactions in the early solar nebula may have nudged the disk. Others propose that the influence of a passing star long ago tilted the system. A more recent and tantalizing hypothesis points toward the possible existence of Planet 9, a massive, unseen world lurking far beyond Neptune. The gravitational tug of such a planet could explain not only the tilt but also the strange clustering of distant icy bodies. If Planet 9 exists, it would itself be a cosmic anomaly, several times the mass of Earth, orbiting in the darkness at distances hundreds of times greater than Pluto. Detecting it would be one of the greatest astronomical achievements of our time, reshaping our understanding of the solar system's dynamics. Until then, the mystery of the tilt remains unsolved, a subtle yet persistent reminder that even in our celestial backyard, anomalies abound. From the tilt of the solar system, we leap into the bizarre phenomenon of cosmic rays, high-energy particles that streak through the universe at nearly the speed of light, bombarding Earth from every direction. Most originate from supernovae and other energetic astrophysical events, but the most powerful cosmic rays defy explanation. These ultra-high-energy cosmic rays carry energies millions of times greater than those produced in human-made particle accelerators. Their sheer power is staggering, a single proton with the energy of a well-hit baseball, condensed into a subatomic particle. But where do they come from? Some point to active galactic nuclei or gamma-ray bursts as possible sources, while others suggest more exotic origins, decay of hypothetical particles left over from the early universe, or even processes involving dark matter. What deepens the mystery is that these particles interact with cosmic background radiation, meaning they shouldn't be able to travel far before losing energy. Yet we detect them, implying either nearby extreme sources or new physics at play. Cosmic rays also carry practical consequences. They pose hazards to astronauts, damage satellites, and influence Earth's atmosphere. But as anomalies, they serve a deeper role. They are nature's particle accelerators, probing energies and interactions far beyond the reach of our laboratories. Each one striking Earth may hold a clue to forces that shape the universe itself. As we explore the skies, one of the strangest stellar anomalies we encounter is Tabby's star, also known as KIC 8462852. Discovered through data from the Kepler Space Telescope, this otherwise ordinary-looking star displays baffling patterns of dimming, sometimes fading by as much as 20% over short periods. For comparison, when a planet transits its star, the dimming is typically less than 1%. The sheer irregularity of Tabby's star's dips confused astronomers. Could massive clouds of dust be passing in front of it? Could the star itself be undergoing unusual internal processes? Some explanations suggested swarms of comets breaking apart and obscuring the light. Yet none of these ideas fully match the data. This led to one of the most provocative hypotheses: could the dimming be caused by a megastructure, perhaps a Dyson swarm built by an advanced alien civilization? While this idea captured public imagination, evidence remains lacking. Infrared observations that might reveal waste heat from such a structure show nothing unusual. Despite the fading of that sensational idea, the star's behavior continues to defy full explanation. Tabby's star remains a symbol of astronomical humility, a reminder that even nearby stars can harbor mysteries that stretch beyond the boundaries of current science. From a single mysterious star, we widen our scope to entire star clusters, some of which display anomalies of their own. Globular clusters, ancient spheres containing hundreds of thousands of stars, are relics of the early universe. Yet, when studied closely, they reveal chemical compositions that defy expectations. Traditionally, astronomers believed all stars in a given cluster formed at the same time from the same material. But observations show multiple stellar populations with different chemical signatures. Some stars contain unusual amounts of helium, while others show variations in heavier elements. How could one cluster host such diversity? Theories range from successive waves of star formation triggered by supernovae to exotic mixing processes within the cluster. But the uniform appearance and great age of globular clusters make such explanations difficult. Perhaps the answer lies in interactions with the galaxies they orbit, or in processes we do not yet understand. Beyond their chemistry, some clusters also host black holes or neutron stars in numbers that seem anomalous, hinting at violent pasts of collisions and mergers. Far from being static stellar fossils, globular clusters may be dynamic laboratories where cosmic processes play out in unexpected ways. Shifting focus once more, we encounter the enigma of cosmic radio loops, vast, mysterious structures in the sky that emit radio waves. One of the largest, Loop I, spans a huge portion of the celestial sphere. At first glance, these loops might seem like remnants of ancient supernova explosions, expanding bubbles of gas and energy. Yet their size, brightness, and symmetry raise more questions than answers. The difficulty lies in determining their true distance. Some may be relatively close, within our own galaxy, while others could stretch across intergalactic scales. Without precise measurements, their origins remain uncertain. Are they the fossil remains of massive star-forming events, or signatures of even more exotic phenomena, like magnetic fields on galactic scales? Adding to the mystery, not all loops fit neatly into the supernova model. Their structures are often too large, too uniform, or too persistent to match the behavior of typical remnants. Instead, they may represent processes we don't yet fully grasp, perhaps linked to interactions between cosmic rays, plasma, and magnetic fields over millions of years. Cosmic radio loops remind us that the sky, even when mapped in detail, still hides vast structures whose stories remain untold. They are whispers across the electromagnetic spectrum, signals of ancient cosmic dramas still echoing in the present. From the vast radio loops of our galaxy, we turn to the chilling enigma of the Boötes void, a region of space so empty it seems almost unnatural. Spanning over 330 million light-years across, this cosmic desert contains remarkably few galaxies compared to its immense size. To peer into the Boötes void is to gaze into near-nothingness, a cosmic abyss where creation seems absent. The question is, how did such an enormous void form? Standard models of cosmic structure predict voids as part of the universe's web-like pattern, but the Boötes void is unusually large, far beyond expectations. Some scientists propose that smaller voids merge together, leaving behind this giant scar of emptiness. Others wonder if it signals flaws in our understanding of cosmic evolution. From an observational perspective, the Boötes void is unsettling. Galaxies inside it are rare and isolated, like lonely islands in a vast ocean. Life in such galaxies, if it exists, would know a night sky stripped of the rich tapestry we see on Earth, just a few faint smudges of light scattered in an overwhelming dark. The Boötes void reminds us that anomalies aren't always about excess, sometimes they are about absence. In the silence of emptiness lies one of the universe's most profound mysteries. Another anomaly-defying explanation is the existence of galaxies without stars, so-called dark galaxies, which we touched on earlier, but deserve deeper exploration. Unlike traditional galaxies filled with billions of shining suns, these entities are composed primarily of dark matter and cold gas. Only faint radio emissions from hydrogen reveal their presence. One candidate, known as Virgo He21, lies within the Virgo cluster. It contains a vast amount of hydrogen gas, yet shows no evidence of significant star formation. How can such a massive reservoir of material fail to ignite into stars? One possibility is that its gas is too diffuse, unable to collapse under gravity. Another is that interactions with nearby galaxies stripped it of the conditions needed to spark stellar birth. If dark galaxies are common, they may represent a hidden population shaping galactic evolution in ways we have barely considered. Their invisible presence could account for many of the discrepancies we see in cosmic structure. And they raise philosophical questions: can we call them galaxies at all if they contain no light? In their silence, dark galaxies are anomalies that redefine our understanding of what a galaxy truly is. They may be ghosts, failed creations, or silent architects shaping the universe from the shadows. Perhaps the most mind-bending anomalies are not objects at all, but patterns, specifically, the cosmic alignments found across vast stretches of space. One of the most famous is the so-called axis of evil in the cosmic microwave background, CMB. This strange alignment of temperature fluctuations across the sky appears to contradict the assumption that the universe is isotropic, that it looks the same in all directions. If the axis of evil is real and not an artifact of measurement, it could point to something profound, perhaps a preferred direction in the cosmos, or evidence of structures beyond our observable horizon. Such a finding would challenge one of the bedrock principles of cosmology, forcing us to rethink the very framework upon which our models are built. Other alignments deepen the mystery. Quasars separated by billions of light-years sometimes display their spins in correlated directions. Large-scale galaxy distributions also hint at subtle patterns across regions too vast for chance to explain. Are these alignments clues to a deeper cosmic order? Or are they statistical flukes amplified by our limited perspective? Until we understand them, they remain anomalies, threads in the tapestry of the cosmos whose pattern we have not yet unraveled. Among the most haunting celestial enigmas are supermassive black holes that should not exist. Astronomers have discovered quasars hosting black holes billions of times more massive than the Sun, yet these monsters were already fully formed less than 1 billion years after the Big Bang. According to standard models, black holes should grow gradually, feeding on gas and merging with others over eons. So how did such titans appear so quickly? Some theories suggest that these objects formed through direct collapse, skipping the stellar phase altogether. Massive clouds of primordial gas could have collapsed straight into black holes hundreds of thousands of times the Sun's mass. Others argue that early conditions in the universe, perhaps influenced by exotic physics, allowed for accelerated growth. These supermassive black holes are anomalies not just because of their size, but because of their timing. Their existence hints at processes we do not yet understand, processes that may have shaped the very first galaxies. They force us to question whether our models of the early universe are incomplete, or whether nature has shortcuts we have yet to uncover. In their silent enormity, these ancient giants stand as paradoxes, impossibly massive relics of a time when the universe itself was still a child. Another anomaly comes from the edge of cosmic observation, ultra-diffuse galaxies that somehow host supermassive black holes far too large for their size. Normally, the mass of a galaxy's central black hole is correlated with the mass of the galaxy itself. Yet some dwarf or faint galaxies contain black holes millions of times heavier than expected, as though the central engine grew without regard for its surroundings. This mismatch poses a puzzle. Did the black hole form first, with the galaxy struggling to assemble around it? Or were these galaxies once much larger, stripped of their stars through violent interactions, leaving only a black hole disproportionately dominating what remains? One striking example is the galaxy NGC 4395, which is relatively small but harbors an active black hole. Observations like this suggest that the relationship between galaxies and their central black holes may be far more complex than a simple scaling law. These anomalies hint at chaotic histories, galaxies merging, cannibalizing one another, and leaving behind remnants that defy prediction. They show us that the universe does not build its structures neatly, but rather through collisions, disruptions, and exceptions that leave behind cosmic riddles. Perhaps one of the strangest anomalies of all lies not in deep space, but in the fundamental constants of nature. Physics rests on numbers that appear fixed: the speed of light, the gravitational constant, the fine structure constant that governs electromagnetic interactions. These values seem immutable, written into the laws of the cosmos itself. Yet some observations suggest they may not be entirely constant. Quasar absorption spectra, light passing through intergalactic gas, hint that the fine structure constant may vary slightly across vast distances. If true, this would imply that the laws of physics are not uniform everywhere, but subtly shift depending on where you are in the universe. Such a revelation would shatter one of the core assumptions of modern science, that the laws of nature are universal. Even tiny variations in these constants would have profound implications. Stars might burn differently, chemistry might not unfold the same way, and life as we know it might never arise. The universe we inhabit could be just one version among countless possible realities shaped by different numbers. Though still debated, the possibility that physical constants vary transforms them from absolutes into anomalies. They remind us that the bedrock of physics may not be as unchanging as we believe, but rather part of a deeper, evolving story written across the cosmos. Among the most intriguing anomalies in astrophysics are gravitational lenses that bend light more strongly than expected. According to general relativity, massive objects like galaxies or clusters bend the path of light from background objects, producing arcs, rings, or multiple images. This phenomenon allows astronomers to map mass distribution, including invisible dark matter. Yet, in some cases, the bending is far stronger than predicted by visible matter alone. Clusters of galaxies sometimes magnify background light to extremes, implying far more mass than detected. These overlensing events suggest either unusual concentrations of dark matter or something stranger, perhaps flaws in our understanding of gravity itself. Even more curious are rogue gravitational lenses, small, faint objects that act as lenses despite showing little evidence of sufficient mass. Could they be compact dark matter clumps, or exotic forms of matter we have yet to detect? Gravitational lensing is one of the most powerful tools in modern astronomy, yet its anomalies remind us that even phenomena predicted by well-tested theories harbor secrets. Each distorted image in the sky is not just a beautiful arc of light, but also a riddle written across space-time itself. While gravitational lenses magnify the distant universe, another anomaly shrinks it in ways we struggle to explain. Ultra-compact dwarf galaxies. These objects are far smaller than typical galaxies, yet contain enormous numbers of stars packed into incredibly dense regions. Some harbor black holes far larger than expected, as though they are the stripped cores of ancient galaxies that lost their outer layers. Their origins are debated. Did they form as oversized star clusters that grew unusually massive? Or are they remnants of galaxies torn apart by tidal forces, leaving behind only their central bulges? Their chemical composition suggests long, complex histories, but their small sizes defy the conventional categories of galaxy or star cluster. Some ultra-compact dwarfs show evidence of multiple generations of stars, implying that they once had far more mass to recycle material through star formation. Others shine unusually brightly compared to their size, hinting at hidden processes of enrichment and collapse. These dense, miniature galaxies challenge our understanding of galactic evolution. They blur the line between stars, clusters, and galaxies, existing as cosmic anomalies that resist simple classification. In their compact brilliance lies evidence of the universe's chaotic past, where collisions and mergers sculpt strange survivors. From compact galaxies we move to an even stranger anomaly, stars that seem too old for the universe itself. Astronomers have identified stars whose ages, based on chemical composition and stellar models, appear to exceed the 13.8 billion-year age of the cosmos. While refinements in measurement often reduce these discrepancies, the persistence of such anomalies continues to unsettle. One famous example is the star HD 140283, nicknamed the Methuselah star. Early estimates placed its age at over 14.5 billion years, older than the universe itself. Subsequent refinements lowered its age slightly, but it still hovers near the universe's maximum, pushing the limits of what seems possible. How can this be? Perhaps our models of stellar evolution require adjustment, or our assumptions about early cosmic chemistry are incomplete. It may also point to uncertainties in how we measure the expansion of the universe, tying back to the Hubble tension. If even one star were truly older than the universe, it would shatter our cosmological framework. While the most extreme cases likely stem from measurement errors, the very existence of such candidates keeps the door open for revolutionary discoveries. These ancient suns shine not only with light, but with questions that challenge the boundaries of time itself. The universe often hides its strangest anomalies in plain sight. One such puzzle is found in the category of fast-moving stars, also called hypervelocity stars. These are stars traveling so quickly that they are on trajectories to escape their home galaxies entirely. Some of these stellar projectiles reach speeds of over 1 million kilometers per hour, propelled into intergalactic space. How do they achieve such astonishing velocities? In many cases, the culprit appears to be interactions with supermassive black holes. If a binary star system wanders too close to a black hole, one star can be captured while the other is flung away at tremendous speed. Other mechanisms include violent supernova explosions that send surviving companion stars hurtling through the cosmos. Hypervelocity stars are rare, but their very existence challenges our understanding of galactic dynamics. They provide insight into the hidden processes at the centers of galaxies and the violent interactions that shape stellar populations. For the stars themselves, their journeys are lonely ones. Once expelled, they travel endlessly through the void, with no galaxy to call home. In a sense, they are cosmic exiles, bright but solitary anomalies racing through the darkness, carrying with them the secrets of their violent origins. Equally puzzling are the ghostly rings and shells of galaxies. Vast, faint structures of stars that surround some galaxies like ripples in a pond. Unlike spiral arms or elliptical halos, these rings appear disconnected, often forming concentric patterns around otherwise normal-looking galaxies. Astronomers believe they may be the aftermath of galactic collisions, where a smaller galaxy plunged through a larger one, disturbing its stars and gas. The gravitational shock waves then reorganize the material into rings or shells that persist for billions of years. Yet the precise mechanics remain uncertain, especially for systems with multiple, well-defined shells. These stellar rings are anomalies because they reveal galaxies as dynamic, ever-changing systems rather than static collections of stars. Each shell and ripple is a fossil record of cosmic violence, an imprint of interactions long past. Some galaxies, like Hoag's object, blur the line further, creating perfect, symmetric rings that defy explanation by simple collisions. Are they the product of rare orbital resonances, or do they hint at processes still undiscovered? Whatever the cause, these structures remind us that even galaxies bear scars, silent witnesses to the chaotic ballet of cosmic evolution. From galactic rings we move to a truly exotic idea: primordial black holes. Unlike stellar black holes formed from collapsing stars, primordial black holes may have formed in the very early universe, mere moments after the Big Bang. In those chaotic first instants, density fluctuations could have collapsed directly into black holes of all sizes, from microscopic to billions of solar masses. If they exist, primordial black holes could explain many anomalies. They might account for some or all of the dark matter, their invisible masses silently shaping galaxies. They could also see the growth of supermassive black holes, explaining how such giants appeared so early in cosmic history. Detecting them, however, is extraordinarily difficult. Smaller ones may have evaporated through Hawking radiation long ago, while larger ones hide among ordinary black holes. Some gravitational lensing surveys hint at their presence, but no conclusive evidence has yet emerged. Primordial black holes remain speculative, but their potential is staggering. They bridge the smallest scales of quantum physics with the largest structures in the cosmos. If confirmed, they would not only solve long-standing anomalies but also open new windows into the birth of the universe itself. One of the strangest categories of anomalies are the polar ring galaxies. These rare systems feature a central galaxy, usually lenticular or elliptical, surrounded by a ring of stars, gas, and dust orbiting at a steep angle, often nearly perpendicular to the main disk. The result is a galaxy that looks as though it wears a glowing halo tilted on its side. How do such bizarre formations arise? Astronomers believe they may result from galactic mergers or the capture of material from passing galaxies. Gas stripped during these encounters can settle into polar orbits, eventually forming new stars and giving rise to the distinctive rings. But the anomaly is not just visual. Polar ring galaxies allow astronomers to study gravity from two directions at once. Because matter orbits both around the main disk and across it, these galaxies provide unique tests of dark matter distribution. In some cases, the rings rotate in ways that challenge expectations, suggesting that dark matter halos may be more complex than simple spherical models. Though rare, polar ring galaxies are cosmic laboratories, beautiful anomalies that reveal hidden aspects of galactic dynamics, while also reminding us that the universe sculpts its creations in ways that defy convention. As we peer into the universe with ever more powerful telescopes, another anomaly emerges: galaxies that appear far too mature for their age. Observations of galaxies existing just a few 100 million years after the Big Bang reveal systems already massive, structured, and enriched with heavy elements. According to standard models, galaxies should take billions of years to reach such complexity. The James Webb Space Telescope has intensified this puzzle by uncovering galaxies so bright and massive at such early epochs that they shouldn't exist. Their very presence challenges our understanding of how quickly matter could clump together after the Big Bang. Were early stars and black holes forming faster than expected? Did unknown processes accelerate galactic growth? Some astronomers propose that our cosmological models need revision. Perhaps dark matter interacted differently in the early universe, clumping more efficiently. Or maybe new forms of physics, such as variations in dark energy, played a role. Others suggest we may be underestimating the brightness of certain stellar populations, making galaxies appear more massive than they are. Whatever the answer, these ancient, overgrown galaxies are anomalies that force us to reconsider the timeline of cosmic history. They hint that the universe may have grown up faster than we ever imagined. Closer to home, another anomaly has puzzled astronomers for decades: the Pioneer anomaly. The Pioneer 10 and 11 spacecraft, launched in the early 1970s to explore the outer solar system, began drifting slightly off their predicted trajectories as they journeyed beyond Pluto. The deviation was tiny, an unexplained acceleration toward the Sun, but it persisted, baffling scientists. At first, exotic explanations were considered. Could it be a new force of nature, or evidence that gravity behaves differently at great distances? Could dark matter within the solar system be subtly tugging on the probes? The anomaly even inspired speculation about hidden planets or undiscovered physics. Eventually, careful analysis revealed a more mundane explanation: the spacecraft themselves. Heat radiating unevenly from the probe's power sources created a faint but steady recoil force, gradually altering their paths. In this case, the anomaly was solved not by rewriting physics, but by understanding the spacecraft more precisely. Yet the Pioneer anomaly serves as a lesson. Even tiny deviations in expected behavior can spark revolutionary questions. For years, it pushed scientists to challenge assumptions and consider radical possibilities. In that sense, it remains one of the most influential anomalies in modern space exploration, showing how mysteries, big or small, drive discovery forward. From spacecraft anomalies, we turn to one of the most famous mysteries in radio astronomy, the WOW signal. Detected in 1977 by the Big Ear Radio Telescope in Ohio, it was a powerful, 72-second burst of radio waves from the direction of the constellation Sagittarius. What made it so extraordinary was its intensity and narrowband nature, characteristics consistent with what one might expect from an artificial transmission. Astronomer Jerry Ehrman, who discovered the signal on the data printout, famously circled it and wrote "Wow" in the margin, giving the anomaly its name. Despite decades of follow-up searches, the signal has never repeated, leaving us with a tantalizing one-time event. Numerous explanations have been proposed. Some suggest it could have been a natural astrophysical phenomenon, such as emissions from hydrogen clouds or passing comets. Others argue that its characteristics are too precise to fit known natural sources. While the idea of an extraterrestrial origin remains speculative, the WOW signal stands as one of the best candidates for a potentially artificial message. Its true nature may never be known, but its impact is undeniable. The WOW signal inspired generations of scientists and the public alike to consider the possibility that we are not alone. It remains a symbol of both the promise and frustration of searching for intelligence beyond Earth, a single whisper in the cosmic noise, still unanswered. Not all anomalies come from distant stars or mysterious signals, some arise from our own sun. Though it is the most studied star in the universe, it continues to defy full understanding. One of the greatest puzzles is the coronal heating problem. The Sun's outer atmosphere, or corona, burns at millions of degrees, hundreds of times hotter than the surface below. How can the outer layers be hotter than the source beneath them? This paradox has baffled solar physicists for decades. Leading theories involve magnetic reconnect-ion, where tangled magnetic fields snap and release energy, and waves traveling from the Sun's surface that deposit energy in the corona. Yet no single explanation fully accounts for the observed temperatures. The Sun also produces unpredictable outbursts known as solar flares and coronal mass ejections. These violent events hurl plasma and radiation into space, sometimes disrupting satellites, power grids, and communication systems on Earth. Despite careful monitoring, their precise timing and intensity remain difficult to forecast. Our star, though seemingly ordinary compared to others in the galaxy, hides anomalies that remain unresolved even as probes like the Parker Solar Probe dive ever closer to its fiery heart. It is a reminder that mysteries do not lie only in distant galaxies, they blaze in the sky above us every day. From the Sun's mysteries, we shift to the icy frontiers of the solar system, where another anomaly resides, the tilt of Uranus. Unlike most planets, which spin with axes roughly aligned to the plane of the solar system, Uranus is tipped over by about 98 degrees. It essentially rolls around the Sun on its side, with its poles experiencing decades-long periods of daylight and darkness. How did Uranus end up in such a bizarre orientation? The leading theory is that it suffered a colossal collision with a protoplanet early in its history, knocking it sideways. Yet some simulations suggest that such an impact would have disrupted its moons and rings more dramatically than we see today. Alternative ideas propose that gravitational interactions during the chaotic early days of planetary migration may have slowly tilted it. The consequences of this tilt are profound. Uranus's magnetic field is also strangely misaligned, tilted significantly from its rotational axis. Its weather patterns and seasons are unlike any other planet, with storms and atmospheric dynamics that remain poorly understood. In its quiet strangeness, Uranus is a planetary anomaly, an outlier in a solar system that otherwise follows predictable patterns. Its sideways spin is a cosmic scar, a silent testimony to the violence and chaos that shaped the early solar system. If Uranus stuns with its sideways spin, then Saturn's hexagon is an anomaly of breathtaking peculiarity. Discovered by the Voyager spacecraft in the 1980s and later confirmed by the Cassini mission, this vast, six-sided jet stream circles Saturn's north pole, locked in place for decades. Unlike any atmospheric feature seen on Earth or elsewhere in the solar system, the hexagon spans nearly 30,000 kilometers across, large enough to fit for Earth's inside. What maintains such a precise geometric shape in a swirling gas giant's atmosphere? Laboratory experiments suggest that certain fluid dynamics can create polygonal patterns, but the persistence of Saturn's hexagon remains a mystery. Winds within it reach hundreds of kilometers per hour, yet the hexagonal boundary stays sharply defined. Even stranger, the hexagon appears to change color with the seasons, shifting from blue hues to a golden tone as Saturn's atmosphere evolves. Some theories propose that deep-seated atmospheric waves or interactions with Saturn's rotation are sustaining the structure. Others point to energy exchanges from deeper layers of the planet. Whatever the cause, it demonstrates that even the familiar gas giants harbor atmospheric systems far more complex than our models predict. The hexagon is not just a storm, it is a planetary riddle, a piece of geometry carved into the clouds of a world we thought we understood. From Saturn's geometric storms, we turn to the Kuiper Belt, where anomalies reshape our understanding of the solar system's boundaries. This distant region, home to icy worlds like Pluto, Eris, and Makemake, is not just a reservoir of comets, it is a laboratory of celestial oddities. One of the greatest puzzles is the strange clustering of orbits among distant Kuiper Belt objects, KBOs. Instead of being randomly distributed, many of these icy bodies share similar orbital tilts and orientations. Such clustering hints at the gravitational influence of something massive, perhaps the elusive Planet 9. Estimated to be several times Earth's mass, this hypothetical planet could be lurking far beyond Neptune, shepherding KBOs into their unusual patterns. Despite intense searches, Planet 9 remains undetected. Some scientists argue the clustering may be a statistical illusion or the result of complex gravitational interactions among the known planets. Yet the evidence persists, tantalizing astronomers with the possibility of an undiscovered giant lurking in the darkness. If found, Planet 9 would be one of the most important planetary discoveries in history, expanding our solar system once more. Until then, the Kuiper Belt remains a region where anomalies reign, whispering of hidden worlds yet unseen. As we step even farther into the outer reaches, another anomaly emerges, the strange behavior of interstellar dust and plasma at the edge of the heliosphere, the bubble carved out by the solar wind. The Voyager spacecraft, now traveling through interstellar space, have revealed unexpected findings. At the boundary between the solar wind and interstellar medium, known as the heliopause, scientists expected a smooth transition. Instead, the Voyagers detected complex, turbulent regions, with magnetic fields and particle densities fluctuating wildly. The interstellar medium itself appears denser and more structured than predicted, challenging models of how our solar system interacts with the galaxy around it. Even more puzzling, Voyager 1 continues to detect plasma oscillations far beyond the heliosphere, suggesting that interstellar space is not as quiet as once thought. These waves may be triggered by distant supernovae or other energetic events propagating through the galaxy. The anomaly lies in the unpredictability. The boundary of our solar system was supposed to be relatively straightforward, yet it is proving to be a complex, dynamic frontier. In many ways, the Voyager's discoveries remind us that even the edge of our own neighborhood is filled with mysteries that defy easy explanation. If the edge of our solar system holds surprises, then the realm of exoplanets delivers anomalies beyond imagination. Since the 1990s, thousands of exoplanets have been discovered, and among them are worlds so strange they defy traditional planetary science. One such class are the so-called superpuffs. Superpuffs are planets with masses similar to Earth or Neptune but radii so large they resemble gas giants. Their densities are extraordinarily low, comparable to cotton candy. How can a planet so light hold onto such a vast atmosphere? Some scientists propose they formed far from their stars, in cold regions where volatile gases could accumulate, before migrating inward. Others suggest that strong stellar winds are puffing up their atmospheres to extreme levels. These airy giants orbit in precarious conditions, and their atmospheres may be fleeting, destined to evaporate over cosmic time. Yet while they last, they represent a class of planets unlike anything in our solar system. Superpuffs challenge our assumptions that planets must follow familiar categories of rocky worlds, gas giants, and icy bodies. They remind us that the universe is far more creative than we imagined, crafting worlds that look impossible, yet exist nonetheless. If superpuffs are anomalies of delicacy, then lava worlds are anomalies of ferocity. Take 55 Cancri E, a planet twice Earth's size that orbits so close to its star that a year lasts only 18 hours. Its surface temperatures soar above 2000 degrees Celsius, hot enough to melt rock. Astronomers believe its surface may be covered by vast lava oceans, constantly boiling and reshaping the landscape. Even stranger, 55 Cancri E may experience extreme atmospheric cycles. On the star-facing side, minerals could vaporize, forming an atmosphere of rock vapor. On the cooler night side, that vapor could condense and rain molten rock back to the surface. A planet where it literally rains lava, this is no longer science fiction but science fact. Other lava worlds, like K2-141b, share similar fates, with locked rotations ensuring that one hemisphere bakes eternally while the other freezes in darkness. These planets exemplify how diverse and extreme planetary conditions can be, highlighting the limits of habitability while expanding our imagination of what worlds can exist. Though inhospitable, lava worlds provide invaluable laboratories for studying planetary physics. They are natural experiments in heat, chemistry, and geology taken to extremes, anomalies that teach us about resilience and destruction on a planetary scale. Some anomalies blur the line between planets and stars, brown dwarfs. Too small to ignite sustained hydrogen fusion like true stars, yet too large to be considered planets, brown dwarfs occupy a twilight zone of astrophysics. They glow faintly with heat from gravitational contraction, and some even burn deuterium briefly in their youth, but they are not stars in the traditional sense. The anomaly lies in their diversity. Some are only a few times heavier than Jupiter, while others approach the threshold of full-fledged stars. They exhibit unusual weather, with clouds of molten iron or silicate dust swirling in their atmospheres. Observations of brightness variation suggest storms larger than Earth itself sweeping across their surfaces. Brown dwarfs also defy simple categorization. Do they form like stars, collapsing from clouds of gas? Or do they form like planets, condensing within disks around stars before being ejected? Evidence points to both, leaving them straddling two worlds of formation theory. These cosmic misfits remind us that nature does not always adhere to human-made categories. In the twilight between stars and planets, brown dwarfs exist as living anomalies, challenging definitions while hinting at processes we have yet to fully understand. If brown dwarfs blur categories, then rogue black holes embody cosmic danger in its purest form. Most black holes are found in predictable locations, within galaxies, often at their centers or in binary systems. Yet recent evidence suggests some may wander alone through interstellar space, invisible except for the havoc they wreak on nearby matter. These rogue black holes may be the result of gravitational kicks during supernova explosions or galactic collisions that eject them at incredible speeds. Once adrift, they travel silently, pulling in gas, dust, and even unlucky stars that cross their paths. Astronomers recently detected one such wanderer by the way it gravitationally lensed a background star, bending its light without any visible object present. The danger they pose is chilling. A rogue black hole passing through a star system could disrupt planetary orbits or strip entire systems apart. Though the odds of one approaching our solar system are vanishingly small, the possibility remains, a lurking threat hidden in the darkness between the stars. These anomalies remind us that the universe is not a safe, orderly place. It is dynamic, chaotic, and filled with wanderers that defy both prediction and detection. Rogue black holes are cosmic predators, unseen but ever present, shaping the galaxy in silence. If rogue black holes haunt interstellar space, then stellar nurseries present anomalies of creation. Nebulae like the Orion Nebula or the Eagle Nebula are vast clouds of gas and dust where new stars are born. Yet, despite decades of study, mysteries persist. One puzzle is the efficiency problem. Given the amount of gas present, far more stars should form than we observe. What halts this runaway birth rate? Some propose that powerful winds and radiation from newborn stars blow away surrounding material, quenching star formation. Others point to turbulence and magnetic fields as regulators. But the precise balance remains unclear. Another anomaly is the presence of massive stars. According to theory, radiation pressure from growing stars should halt further accretion of matter, capping their mass. Yet we observe stars dozens, even hundreds of times more massive than the Sun. How do they grow so large against theoretical limits? Stellar nurseries also exhibit structures that defy easy explanation: pillars, filaments, and not sculpted into surreal shapes. These may result from shockwaves of nearby supernovae or interactions with galactic magnetic fields, but the details remain elusive. In these regions, the universe reveals its artistry, sculpting stars, planets, and systems, yet hiding its methods behind anomalies that continue to puzzle. If stellar nurseries are cradles of light, then pulsar timing anomalies are the ticking clocks of the cosmos. Pulsars rotate with astonishing regularity, some more precise than atomic clocks on Earth. Their pulses are so consistent that they are used to test general relativity and even search for gravitational waves. Yet sometimes, these perfect timekeepers stumble. One such anomaly is the glitch phenomenon. Without warning, a pulsar's rotation suddenly speeds up. This is thought to be caused by the transfer of angular momentum from the star's superfluid interior to its crust, but the details are poorly understood. Why glitches occur irregularly, and why their magnitudes vary so widely, remains a mystery. Other pulsars exhibit the opposite effect: sudden slowdowns or unexplained changes in pulse shape. Some even seem to switch off temporarily, their signals vanishing before reappearing later. These erratic behaviors challenge the idea that pulsars are perfectly stable lighthouses. Pulsar anomalies also have practical implications. Networks of pulsars are being used as galactic-scale detectors for gravitational waves. Yet unexplained timing irregularities complicate these efforts, introducing uncertainties that may mask or mimic faint signals. These stellar metronomes remind us that even the universe's most precise clocks are not immune to mystery. Their glitches are whispers from the exotic physics of neutron star interiors, physics we cannot replicate, but can only study through these cosmic anomalies. From pulsar irregularities, we move to another profound anomaly: the missing antimatter problem. According to the laws of physics, the Big Bang should have produced equal amounts of matter and antimatter. Yet, when we look around the universe, we see almost exclusively matter. Antimatter, particles identical to matter but with opposite charge, is nearly absent, appearing only fleetingly in particle accelerators or cosmic ray interactions. Why does the universe prefer matter over antimatter? This asymmetry is one of the deepest unsolved mysteries in physics. If matter and antimatter were truly balanced, they should have annihilated each other long ago, leaving behind nothing but energy. Instead, we exist in a universe made of matter, stars, planets, people, all surviving against the odds. Some theories suggest that subtle violations of symmetry in particle physics tip the scales slightly in favor of matter. Others propose more exotic answers, such as entire regions of the universe composed primarily of antimatter, separated from matter by boundaries we cannot yet observe. This cosmic imbalance is an anomaly not just in astronomy but in existence itself. It is the reason anything exists at all, yet its origins remain hidden in the earliest moments of time. Without it, there would be no galaxies, no life, no story, only empty radiation filling the void. Another puzzle emerges from deep surveys of the sky: the mystery of cosmic acceleration variations. While dark energy is often treated as uniform, some evidence suggests it may not act evenly across space or time. Measurements of distant supernovae and galaxy distribution sometimes indicate small but persistent discrepancies, regions where expansion appears slightly faster or slower than the cosmic average. Are these simply errors in measurement, or hints of something more profound? If dark energy is not constant but dynamic, changing in strength over time or across space, it would reshape our understanding of cosmic evolution. Some theories propose quintessence, a field that evolves slowly and influences expansion differently in different regions. Others suggest interactions between dark energy and dark matter could produce localized effects. The anomalies may also point to something even stranger: that our observable universe lies within a larger multiverse, and that variations we see are imprints of different cosmic regions brushing against one another. For now, these irregularities remain subtle, buried in the noise of data. But if confirmed, they would mean the fate of the universe is far more complex than a simple acceleration. It may be an evolving story still being written across the stars. Closer to Earth, another enigma captivates scientists and storytellers alike: oceans beneath icy moons. Worlds like Europa, Enceladus, and Titan are shrouded in ice, their surfaces appearing frozen and lifeless. Yet evidence suggests vast liquid oceans exist beneath their crusts, warmed not by sunlight but by tidal forces from their parent planets. The anomaly lies in their persistence. How can liquid water exist so far from the Sun, in environments colder than Pluto? The answer may be hidden in gravitational heating. As these moons orbit massive planets like Jupiter and Saturn, their interiors flex and strain, generating heat that keeps water from freezing solid. Even more astonishing are the plumes observed on Enceladus, jets of water vapor and organic compounds erupting from cracks in its icy shell. These geysers suggest a global ocean beneath, possibly in contact with a rocky core that could provide energy and nutrients. On Europa, similar surface features hint at the same phenomenon. These anomalies transform icy moons from frozen wastelands into potential habitats. They may host ecosystems in eternal darkness, warmed by internal energy sources rather than starlight. If life exists there, it would prove that biology is not limited to Earth-like conditions. It thrives wherever water and energy meet. While icy moons may conceal oceans, another planetary anomaly stands in stark contrast: Venus, Earth's twin gone wrong. Nearly identical in size and composition to our own planet, Venus should, in theory, be a habitable world. Instead, it is a hellscape of crushing pressure, scorching temperatures above 460 degrees Celsius, and clouds of sulfuric acid. The anomaly is not just Venus's inhospitable conditions, but how it reached this state. Early in its history, Venus may have had oceans and a more temperate climate. Yet at some point, a runaway greenhouse effect transformed it into the furnace we see today. Carbon dioxide dominates its atmosphere, trapping heat and creating conditions more extreme than any other rocky planet. Adding to the mystery, Venus rotates backward compared to most planets and does so incredibly slowly. Its day is longer than its year. Why this happened is still debated, with theories ranging from catastrophic collisions to tidal interactions with the Sun. Perhaps most intriguingly, anomalies in its atmosphere hint at possible traces of unusual chemistry. Some studies have suggested the presence of phosphine, a molecule that, on Earth, is associated with biological processes. Though controversial and unconfirmed, the very suggestion highlights Venus's role as a planetary puzzle, a world that could once have been like ours, but instead became a warning of planetary fragility. From Venus's inferno, we turn to the outer solar system once more, where Triton, Neptune's largest moon, defies expectations. Unlike most large moons, which orbit in the same direction as their planet's rotation, Triton orbits Neptune in the opposite direction, a retrograde motion that signals a violent past. The anomaly suggests Triton did not form around Neptune, but was likely a captured object, perhaps once a dwarf planet from the Kuiper belt. Its capture would have been catastrophic, disrupting Neptune's original moons and reshaping the system. Today, Triton remains geologically active, with geysers of nitrogen gas erupting from its icy surface, one of the few known active worlds in the outer solar system. Even stranger, Triton's surface is young and smooth, lacking the craters expected of an ancient moon. This suggests ongoing resurfacing processes, powered by internal heat sources we do not fully understand. Some models propose a subsurface ocean beneath its icy crust, making Triton a potential candidate for extraterrestrial habitability. Triton is an anomaly in every respect: its orbit, its activity, its likely violent origins. It stands as a reminder that moons, often overlooked, can be just as complex and mysterious as planets themselves. Beyond our solar system, anomalies emerge in the behavior of galactic magnetic fields. Invisible yet pervasive, these fields thread through galaxies, shaping the motion of gas, influencing star formation, and guiding cosmic rays. But their origins remain mysterious. How did magnetic fields arise in the early universe, and how have they maintained themselves over billions of years? Observations reveal that galactic magnetic fields are surprisingly ordered, stretching coherently across vast distances. In some galaxies, they align with spiral arms, while in others they form intricate, large-scale patterns. The strength of these fields is also puzzling, often reaching levels difficult to explain with standard dynamo theories. Even more enigmatic are the intergalactic magnetic fields detected in cosmic voids, regions almost entirely empty of matter. Their very presence challenges our understanding, as there should be little to generate or sustain them in such barren environments. Magnetic fields are invisible architects of the cosmos, yet their true nature is an unresolved anomaly. They influence nearly every astrophysical process, from the birth of stars to the acceleration of particles, but their origins remain one of the most enduring puzzles in science. If magnetic fields weave unseen structures into galaxies, then cosmic strings represent anomalies at the very fabric of spacetime itself. These hypothetical objects are relics of the early universe, infinitesimally thin, yet immensely dense filaments left over from phase transitions in the moments after the Big Bang. Though never observed directly, cosmic strings could be thousands of light-years long, yet thinner than a proton, with masses so great that a kilometer of string would outweigh Earth. Their gravitational effects would be extraordinary, warping space around them and producing distinctive lensing patterns in the light of background galaxies. Some theorists suggest cosmic strings might produce bursts of gravitational waves as they vibrate or collide, signals that could one day be detected by advanced observatories. Others propose that strings may even serve as seeds for galaxy formation, shaping matter in the early universe. The anomaly is not just their bizarre properties, but their elusive nature. Despite decades of searches, no conclusive evidence has been found. Are they rare, hidden beyond our reach, or do they not exist at all? Cosmic strings remain one of the most tantalizing possibilities in modern cosmology, remnants of the universe's birth, threading through reality like scars from its creation. If cosmic strings remain hypothetical, another class of anomalies is very real: galactic collisions and their unexpected aftermaths. When galaxies collide, one might expect chaos and destruction. Yet instead of obliteration, these cosmic encounters often create order, triggering bursts of star formation and reshaping galaxies into new forms. Some collisions produce striking structures like tidal tails, long streams of stars and gas flung outward by gravitational interactions. Others generate ring galaxies or compact elliptical remnants. But anomalies abound. In certain collisions, stars pass through one another unharmed, while gas clouds crash violently, igniting furious episodes of starbirth. Even more puzzling are fossil galaxies, remnants of ancient collisions embedded within larger galaxies. Their distinct chemical compositions and stellar populations tell stories of mergers billions of years past. Some supermassive black holes are also believed to be the products of galactic collisions, their growth accelerated by the infall of matter during these titanic events. Collisions reveal the paradox of the universe: violence that creates, destruction that seeds beauty. They are anomalies not because they are rare, but because their outcomes often defy prediction, sometimes chaotic, sometimes elegant, always transformative. While galactic collisions reshape the cosmos, another anomaly reveals itself in the faintest whispers of the sky: the cosmic neutrino background. Neutrinos are elusive particles with almost no mass, streaming through the universe in unimaginable numbers. Billions pass through your body every second, yet they interact so weakly with matter that you never notice. The anomaly lies in their role in the early universe. neutrinos were produced in vast quantities during the Big Bang, and their distribution should still linger as a background radiation, much like the cosmic microwave background. Detecting this relic, however, is nearly impossible due to their ghostly nature. What we do detect are neutrinos from supernovae, the Sun, and even distant cosmic sources. Yet occasionally, detectors capture neutrinos of energies so high they defy explanation. Known as ultra-high-energy neutrinos, these particles carry more energy than can be easily accounted for by known astrophysical processes. Their origins remain uncertain, perhaps exotic cosmic accelerators, or even decay of unknown particles. Neutrinos are anomalies because they occupy a shadowy realm between visibility and invisibility, between matter and energy. They are both messengers and mysteries, carrying information from the farthest reaches of the universe, yet guarding their secrets with near-perfect silence. If neutrinos whisper from the depths of the cosmos, then gravitational anomalies in galactic rotation shout across the heavens. The puzzle of galaxy rotation curves, first noted in the 1970s, remains one of the strongest pieces of evidence for dark matter. Stars at the edges of galaxies orbit far faster than visible mass alone can explain, as though held in place by an invisible hand. Yet even within this framework, anomalies persist. Some galaxies show rotation curves that don't match either dark matter predictions or modified gravity theories. Others display unusually flat profiles that extend farther than expected. These outliers highlight gaps in our models of how dark matter distributes itself, or perhaps point to physics beyond the standard model. Adding to the strangeness are dwarf galaxies that seem to defy categorization, some spinning too quickly for their size, others barely rotating at all. These discrepancies force astronomers to constantly refine their simulations, searching for a universal theory that can encompass the diversity of galactic behavior. The anomaly of rotation is not confined to the data, it strikes at the heart of cosmology. Either dark matter is more complex than imagined, or gravity itself behaves differently on galactic scales. Each orbiting star is not just a celestial dance, but a clue to the invisible forces shaping the universe. If galaxies test our understanding of gravity, then gravitational wave backgrounds hint at mysteries we are only beginning to perceive. While individual wave events from black hole or neutron star mergers have been detected, astronomers now search for the faint hum of countless overlapping signals, the background soundtrack of the universe. Recent data from pulsar timing arrays suggests the first hints of such a background, with pulsars across the galaxy showing subtle timing shifts consistent with long-wavelength gravitational waves. If confirmed, this would open an entirely new window into cosmic history. But anomalies lurk within the data. The signals appear slightly stronger or weaker in different directions, raising questions about their true origin. Could they be the product of supermassive black hole binaries across the universe? Or are they signatures of exotic phenomena like cosmic strings or phase transitions in the early universe? The gravitational wave background is like static on a cosmic radio. Hidden within it may be messages from the universe's deepest epochs, whispers of processes we cannot yet see. The anomaly lies not only in its detection, but in the profound possibilities it holds for rewriting our understanding of the cosmos. From waves we turn to light, and to one of the strangest observations of all, stars that seem to disappear. Astronomers comparing photographic plates from decades past with modern surveys have found cases where stars once recorded simply no longer appear. These vanishings cannot be explained by ordinary stellar evolution, which unfolds over millions or billions of years. What could cause a star to vanish on human timescales? One possibility is that they were misidentified or obscured by dust. Another is that they collapsed directly into black holes without a visible supernova, a process known as a failed supernova. In such cases, the star's core collapses quietly, leaving little more than a fading infrared afterglow. Even stranger possibilities linger. Could some of these vanishings be the result of rare, exotic processes, or even phenomena we have yet to imagine? A handful of researchers have even speculated, cautiously, that such disappearances could hint at artificial activity, such as civilizations harnessing entire stars for energy. Whatever the cause, disappearing stars are anomalies that remind us that the night sky is not as permanent as it seems. Even the stars themselves can vanish into silence, leaving us with unanswered questions written in the gaps between the constellations. If stars can disappear, then the discovery of stars too massive to exist challenges theory in another direction. Stellar physics predicts an upper mass limit of around 150 solar masses. Beyond this, radiation pressure should blow away material before the star can grow larger. Yet observations of certain clusters, such as the R136 star cluster in the Large Magellanic Cloud, reveal stars estimated at more than 200 or even 300 times the Sun's mass. How do such giants defy the limits? One explanation is stellar mergers. In dense clusters, massive stars may collide, combining into single hypermassive objects. Another possibility is that our models underestimate how radiation pressure interacts with gas in extreme conditions. These enormous stars burn furiously, living only a few million years before collapsing into black holes or exploding in rare hypernovae. They also flood their environments with ultraviolet radiation, shaping star formation in their vicinity. The anomaly of supermassive stars lies not only in their existence but in their implications. They may serve as progenitors for some of the earliest black holes in the universe, bridging the gap between stellar deaths and the seeds of quasars. In their short, furious lives, they embody the extremes of creation and destruction. While some stars grow impossibly large, others shine with puzzling rhythms. The phenomenon of variable stars is well known, with brightness changing due to pulsations, eclipses, or eruptions. Yet certain variables defy these categories, flickering or dimming in ways that challenge explanation. One such case is the enigmatic class of coronae borealis stars. These rare giants fade unpredictably, sometimes dimming by several magnitudes before slowly returning to brightness. The leading explanation involves clouds of carbon dust forming and briefly blocking their light, but the precise triggers remain unclear. Other anomalies include stars that brighten suddenly without clear cause, or objects like Boyajian star, Tabby's star, which exhibit complex, irregular dimming patterns. While dust and debris may account for some behaviors, others remain unexplained, leaving open questions about unseen companions, unusual stellar processes, or even more exotic ideas. Variable star anomalies remind us that even seemingly simple measurements, brightness over time, can uncover mysteries. Stars are not static beacons but dynamic entities, their flickers and fades carry encoded messages about processes we do not yet fully grasp. On galactic scales, another enigma looms: the discovery of galaxies with almost no stars at all. These so-called ultra-diffuse galaxies, UDGs, spread their meager stars over vast areas, making them appear faint and ghostly. Some are as large as the Milky Way but contain only a fraction of its stars, glowing like pale shadows in the night. The anomaly is their formation. How can galaxies this large be so empty? Some theories suggest they are failed giants, their star formation quenched early by supernova feedback or interactions with their environments. Others propose they are heavily dominated by dark matter, which prevents gas from collapsing efficiently. Adding to the mystery, some UDGs appear to lack dark matter altogether, contradicting the very idea that dark matter is essential for galaxy stability. These conflicting observations highlight the diversity of these strange systems, suggesting that multiple formation pathways may exist. Ultra-diffuse galaxies are cosmic ghosts, scattered across clusters and voids alike. Their existence challenges simple narratives of galactic evolution and forces us to consider the hidden complexity of structures that, at first glance, appear almost invisible. Among the most unsettling anomalies in cosmology is the Great Wall of Galaxies. Discovered in the late 1980s and expanded upon in later surveys, these colossal structures stretch across hundreds of millions of light-years, weaving galaxies into walls and filaments that dwarf imagination. The Sloan Great Wall spans over 1.4 billion light-years, while the Hercules Corona Borealis Great Wall extends even farther, more than 10 billion light-years across. These immense formations defy our expectations. According to the cosmological principle, the universe should appear relatively uniform on the largest scales. Yet the existence of such vast, coherent structures suggests otherwise. How could galaxies organize themselves into patterns so enormous within the limited time since the Big Bang? Some argue these walls may be illusions, artifacts of how we survey the sky. Others suggest they represent genuine features. Evidence that gravity and dark matter worked far more efficiently than we believed, or that large-scale structures are influenced by physics beyond current models. Whatever their origin, the Great Walls are anomalies that force us to reconsider scale itself. They remind us that the universe is not evenly sprinkled with galaxies but sculpted into a cosmic architecture whose full design we are only beginning to glimpse. While galaxy walls stretch across the cosmos, other anomalies shrink to the smallest scales, microlensing events that suggest unseen populations of objects in our galaxy. Microlensing occurs when a massive object passes in front of a distant star, bending its light and briefly magnifying it. Most events can be explained by known stars or planets, but some are too strong or too frequent to match expectations. These unexplained microlensing events may point to hidden populations of black holes, brown dwarfs, or even primordial black holes drifting through the galaxy. Some detections suggest masses consistent with objects as small as Earth but completely invisible, candidates for exotic forms of dark matter. The anomaly lies in their abundance. If too many events are caused by unseen objects, our models of galactic mass distribution may need revision. Alternatively, we may be glimpsing hints of entirely new populations of compact bodies, previously undetected. Microlensing anomalies are fleeting, flashes of distortion in a star's light curve. Yet within them may lie the keys to dark matter, black hole populations, or other hidden features of the Milky Way. They are momentary distortions that hint at enduring mysteries. From tiny distortions of light, we move to vast, violent phenomena, galactic winds. These colossal outflows of gas, dust, and energy blast outward from galaxies at thousands of kilometers per second, driven by starbursts or supermassive black holes. While their existence is well established, their scale and effects remain anomalous. Some galactic winds are powerful enough to sweep entire galaxies nearly clean of gas, halting future star formation and transforming them into quiescent, dead systems. Others enrich the intergalactic medium with heavy elements, spreading the ingredients for future stars and planets. Yet the processes behind their intensity remain poorly understood. Why do some galaxies unleash winds strong enough to alter their evolution, while others remain calm? The balance between stellar feedback, black hole activity, and dark matter halos appears delicate and complex. Observations show winds extending hundreds of thousands of light-years, structures so vast they rival the galaxies themselves. Galactic winds are anomalies because they blur the line between internal and external processes. They show that galaxies are not isolated islands but engines interacting dynamically with their surroundings, sculpting the universe on scales both intimate and immense. Among the strangest anomalies in astrophysics are double pulsar systems. Pulsars are already remarkable, neutron stars spinning rapidly and emitting beams of radiation like cosmic lighthouses. But when two of them orbit one another, they create one of the most extreme laboratories for testing the laws of physics. The most famous is PSRJ 07373039, a system where both neutron stars are visible as pulsars. They orbit each other every 2.4 hours, moving at incredible speeds and generating gravitational waves that gradually shrink their orbit. The precision of their pulses allows astronomers to measure effects predicted by general relativity with unprecedented accuracy, such as time dilation, orbital decay, and gravitational redshift. Yet anomalies remain. In some double pulsar systems, timing irregularities cannot be fully explained by current models. Subtle deviations hint at unknown physics, or at least at complexities in neutron star interiors that remain beyond our reach. These systems are cosmic laboratories, where gravity is so intense that it bends time itself. They stand as natural experiments, offering clues not only to the fate of compact objects but also to the fundamental workings of the universe. Double pulsars are not merely rare, they are anomalies that let us peek behind the curtain of space-time. While double pulsars test relativity, another anomaly challenges our models of the cosmos itself: dark flow. In 2008, researchers analyzing data from the Wilkinson Microwave Anisotropy Probe noticed something strange. Clusters of galaxies appear to be moving together in a common direction at high speeds, as if being pulled by something beyond the observable universe. This motion, dubbed dark flow, extends across billions of light-years, suggesting a gravitational influence outside our cosmic horizon. Could it be the imprint of structures beyond the visible universe, tugging on matter we can see? Or is it an artifact of measurement, a subtle distortion in our interpretation of the cosmic microwave background? If real, dark flow could be evidence of something profound, perhaps other universes pressing against our own, or colossal structures existing beyond what we can observe. The idea remains controversial, with some studies questioning its existence while others find supporting hints. Dark flow is an anomaly that forces us to confront the limits of observation. It suggests that what we see may only be part of a larger reality, with unseen forces shaping the motion of galaxies like waves from a hidden ocean. If dark flow hints at forces beyond our horizon, then cosmic isotropy anomalies challenge the assumption that the universe looks the same in every direction. According to the cosmological principle, no matter where we look, the universe should appear statistically uniform on large scales. Yet observations suggest subtle violations of this symmetry. For instance, galaxy counts and quasar alignments show patterns that seem oriented toward specific directions, rather than being random. Even the cosmic microwave background displays temperature fluctuations that appear oddly aligned, features like the so-called axis of evil, which suggest a preferred cosmic direction. Are these alignments real, or simply statistical flukes amplified by our limited vantage point? If real, they could indicate that the universe has a large-scale structure or anisotropy, contradicting the bedrock assumption of cosmology. Some theories propose that inflation, the rapid expansion of the early universe, may not have been perfectly uniform, leaving behind subtle imprints that we now detect. These anomalies remind us that the universe may not be as smooth as our models assume. Instead, it may carry scars of its earliest moments, written across the sky in alignments that whisper of deeper truths beyond our current understanding. Not all anomalies are colossal. Some are fleeting bursts of mystery known as transient luminous events. These phenomena, observed in planetary atmospheres and even across interstellar space, include fast flashes, arcs, or unexplained glows that defy simple categorization. In Earth's skies, sprites and elves are luminous bursts high above thunderstorms, only discovered in recent decades thanks to sensitive cameras. They reveal that even our own planet's atmosphere hides surprises. Beyond Earth, astronomers detect fast optical transients, brief, bright flashes in deep space that vanish as quickly as they appear. Some are tied to supernovae or gamma-ray bursts, but others resist classification entirely. These anomalies test the limits of observational astronomy. Our instruments capture them in seconds, sometimes even fractions of seconds, leaving little time for detailed study. Yet in those moments, they carry signatures of powerful processes unfolding across the cosmos. They remind us that the universe is dynamic, not static. Stars flare, galaxies collide, and mysterious flashes erupt without warning. In their brevity lies both frustration and wonder, cosmic phenomena that appear, astonish, and vanish before we can fully understand them. Beyond fleeting flashes lies a slower, subtler anomaly, the cosmic acceleration of time itself. While relativity explains how time warps under gravity or motion, recent precision measurements hint that the universe's expansion may subtly alter the very way we measure cosmic time. Astronomers observing distant quasars and spectral lines note small discrepancies in how time-dependent phenomena unfold across vast distances. Are these simply artifacts of calibration, or hints that cosmic expansion leaves fingerprints not only in space but in time itself? Some propose that dark energy, far from being a static pressure, may influence the passage of time differently across the cosmos. If true, it would mean that the universe does not just expand spatially, but temporally. Different regions may experience the flow of time at subtly different rates, creating a tapestry of temporal variation stitched into the cosmic web. Though highly speculative, such anomalies remind us that time, perhaps our most fundamental concept, may not be as absolute as we believe. The universe may not only shape space but sculpt the river of time itself in ways we are only beginning to glimpse. Our journey ends with the grandest anomaly of all, the unknown beyond the cosmic horizon. The observable universe stretches 46 billion light-years in every direction, bounded not by walls but by the finite speed of light and the age of the cosmos. Beyond that horizon, we cannot see, but physics suggests there is more. Perhaps infinitely more. What lies beyond? It could be more of the same, endless galaxies, stars, and cosmic webs stretching forever. Or it could be regions with different laws of physics, shaped by variations in fundamental constants. Some theories suggest parallel universes, pocket realities spawned by inflation, each with its own version of existence. Others imagine domains where matter never formed, where only radiation or exotic states of energy reign. This ultimate anomaly is one we cannot measure directly. It sits forever just out of reach, hidden by the boundaries of space and time. Yet it is also the most profound mystery, the possibility that everything we know, every galaxy, every star, every thought, is but a small fragment of a far greater whole. The horizon does not mark the end of the universe. It marks the edge of our understanding, the line where knowledge fades into wonder. And so, we come to the end of our voyage through mind-blowing space anomalies. From black holes that warp reality to stars that vanish without warning, from icy moons hiding oceans to the invisible forces of dark matter and dark energy, each anomaly is a reminder that the universe is stranger than we can imagine. Science thrives on these mysteries. Every unexplained signal, every irregular orbit, every unexpected flash pushes us forward, demanding that we look deeper, measure more carefully, and dare to question our assumptions. Perhaps some anomalies will one day be explained, folded neatly into new theories. Others may remain forever beyond our grasp, eternal riddles woven into the fabric of existence. But all of them serve the same purpose, to remind us that the cosmos is not solved, not finished, not closed. The universe is alive with enigmas, and in its silence, it calls us to seek, to wonder, and to dream. For as long as we ask questions, the story of discovery will never end.